Hello students, in this lecture we are going to discuss about how to determine the transfer function of mechanical systems. We'll start with translational mechanical system. So here we'll discuss what are the different elements that we need to determine in order to get the mathematical modeling of a mechanical system or a translational mechanical system. Then we'll discuss about the rotational mechanical system and we'll be determining the various elements that we need to find the mathematical model of the system. Then at the end, we'll discuss a few examples and we'll try to find the transfer function of a mechanical system. So let's start. So whenever we are having a mechanical system and if we want to describe a given mechanical system, so we need to know what is the mass of that system, what is the stiffness property of that system, and what is the energy dissipating elements that we are having in that system. So if we know these three elements of any mechanical system, we can describe that mechanical system with the help of mathematical equation. So in order to model any mechanical system, we need to find what is the mass of that system, what is the stiffness, that is spring element associated with that system, and then energy dissipating element, so that is damping element in that mechanical system. So if we have all these three elements for any system, we can describe it with mathematical equation, or we can get the mathematical modeling of that mechanical system. Now we know that mechanical system we can classify it as translational. So in translational system, mass is going to move linearly. Okay, and we can also have mechanical system classified as a rotational mechanical system. So there mass is going to rotate. So in this way, we can have two category of mechanical system: translational as well as a rotational mechanical system. So let's discuss about the translational mechanical system. So whenever we want to have a mathematical model of translational mechanical system, we need to find the force contribution of all these three elements in the system. So let's discuss mass first. So when we are having a mass in translational system, it can move linearly. So when we are applying force, so this force will be resisted by the inertia force. So whenever we want to know the force contribution of the mass, so it will be equal to or proportional to its inertia force. So we write it as F is equal to ma, or we can write it as F is equal to mx double dot. So here x is associated with the position of mass. So initially we can mark a start point. So this point where we are having all the mass is concentrated, so it may be the center of mass. So that position we can decide as our starting position. So when mass is going to move, with respect to that, we will be having associated velocity and also acceleration associated with it. So here mx double dot represent this acceleration of mass. Similarly, we can also write it as md square x by dt square. So in this way, we can represent a force contribution of the mass. Now, next element, we are having a spring element that represent a stiffness of that system. So we represent the spring element in this way, and here one end is fixed. So this one is the fixed end, and this one is the free end here. So when we are going to apply some force at this free end, and say this free end is moved by some distance, say the distance is x. So the force that is stored, or the force that this spring is going to develop, will be proportional to this distance. So we can write it as F of spring will be proportional to x. So when we remove this proportionality sign, it will be replaced by K, that is the stiffness of the spring, and into x. So in this way, we can find the force contribution of this spring element that represent the stiffness of the mechanical system. Similarly, other element that we are having is a damper. So damper we represent in this way. So when we are going to apply force to the damper, the force that will be exerted by this damping element will be proportional to the velocity of this damper. So it will be x dot here, as we are considering the reference as x. So velocity will be x dot and acceleration will be x double dot. So it will be force exerted by this damper, or you can say resistive force exerted by this damper, will be proportional to the velocity. So when we remove proportionality sign, it will be c into x dot. So this c is nothing but the damping constant of that system. So in this way, we can find the force contribution of all these elements, and with the help of governing equation, we can determine the equation of motion, or you can say mathematical model of a given mechanical system. Now let's discuss about the rotational system. So again, in rotational system, we will be having mass, and that is represented by a circular element. So we will be having mass. So now here the mass is rotating, and when we apply the torque, so when we talk about the rotational system, we are having torque instead of a force. So when we apply torque, so the resistive force that is offered by this mass will be proportional to its mass and acceleration. So that we write as torque will be equal to J into alpha. So here J is the moment of inertia since it is a rotating object. So we are having moment of inertia as J, and alpha is the acceleration, or we can write it as J into theta double dot, and similarly we can have we can write it as J into d square theta by dt square. So in this way we can represent the torque contribution. Okay, so when we are having a rotational system, we always focus on the torque contribution of each of the element. Okay, so same way, let's discuss about the spring. So again, here spring will be a rotational spring. So when we are going to apply a torque, we will be having a resistive torque. So that resistive torque will be proportional to, so this torque offered by this spring will be proportional to this displacement. Okay, as we had in the case of linear spring also. So it is proportional to the displacement. So here it will be torque is proportional to theta. Similarly, when we remove this proportionality sign, it will be T is equal to K theta. Okay, so this is the torque contribution by this spring element. Similarly, when we talk about the damper, so when we apply torque to this rotating damper, so it is going to exert a reactive torque, and that torque will be proportional to the velocity again here. So it will be an angular velocity, that is theta dot. So when we remove the proportionality, so this torque is equal to C into theta dot. Okay, so in this way we can determine the torque contribution of all the element in rotating system or in rotational system. So now by applying the physical law that the system is going to follow, we can determine the equation of motion or mathematical model of rotational system. So let's take up the example of each of these system and see how we can determine the equation of motion or mathematical model of the system. So let's take an example where we are having a linear system. In this way, we are having a spring and mass is attached to this spring, and also to this mass we are having a damping element that is attached. Say this spring is having stiffness of K, and this damper is having damping constant of C, and we are having a force which is acting on this system in this direction, that is F. And we are having a reference for this mass motion, that is from the center of this mass in this direction X. So now we have to find the transfer function for this system. So whenever we are having this kind of a system, what we need to do, we need to draw the free body diagram. We need to represent mass and all the forces that is acting on that mass. Okay, and then after that we can apply the physical law that it is following, and based on that we can get the mathematical model. So let's first draw the FBD, so free body diagram. So we will be having mass first, then we are having, since force is acting in downward direction, so of course displacement of mass is also going to happen in the downward direction. When mass is moving in the downward direction, this spring as well as this damper will going to resist this force. So they are going to apply force in a reverse direction. So force for this spring we will be having in opposite direction to the force which is acting on the system, that is F. Okay, so this force, we know that spring force, we write it as K into the displacement, that is this X. Similarly, this damper is also going to apply the resistive force, and we know that it is proportional to velocity, so it will be C into X dot. Now, once we have placed all the forces on a mass, so that represent our free body diagram for that system. Now, once we have drawn the free body diagram, now we have to look for the physical law that it is going to follow. So normally we use Newton's law, so that we are going to use here, and that is sum of forces is equal to mass into acceleration. Okay, so here what we have to do, we have to find all the forces and we need to write it on left hand side, and that will be equal to the inertia force of this mass. Now here we need to define the sign of the forces. So the force that is acting in the direction of motion, that is this one downward, so that force we will be considering as positive, and opposite to this motion will be negative force. So here if we write this F force that is acting on this system, so it will be positive, it is positive. Next, this kx and this cx dot, they are acting in opposite to the motion, so they will be considered as negative here. So we will be having minus cx dot minus kx, and that is equal to mx double dot. Now what we will do, we'll send these two forces on right hand side, and we will be writing in this way. So F is equal to mx double dot plus cx dot plus kx. So this equation represents the governing equation. Now we need to find the transfer function. So we know that what we have to do, once we got the equation of motion of the system, we need to apply a Laplace transform. So we will be applying a Laplace transform to this equation. So when we'll apply the Laplace transform to this function, which is right now in time domain, so it will be written as f of s is equal to, m is a constant term, so it will be as it is. Then we are having a differential term. So we know that when we are having differential term like this one that we are having here, how to take Laplace of it. So it is Laplace of d square x by dt square. So it will be represented as s square into x of s, and other term is related to boundary condition, and in transfer function we neglect it. So once we take the Laplace transform of x double dot, it will be s square into capital X of s. Similarly, plus c, and again we are having x dot, so Laplace transform of it will be s into x of s. Now next time we are having kx, so k is again constant, and when we take Laplace of x, it will be capital X of s. Now here we are having x of s in all the terms, so we can take it out. So it will be fs is equal to ms square plus cs plus k into x of s. Now we can write this equation in the form of transfer function, that is output upon input. So output here is x of s, and input that we are having is the force which is acting on the system, this force F. So it will be the input f of s. Now, so this term we can write it as 1 by ms square plus cs plus k. So this is the transfer function for this translational mechanical system. Now let's consider another question that is on rotational mechanical system. So we can consider a shaft that is having some mass, and it is rotating inside a bearing. Say that this is the bearing. So now we are applying some torque onto it, and it is having its moment of inertia, and because of the torque it is rotating. So say that rotation we are representing here in terms of theta. So this system is having a stiffness of K, and the damping that is offered in this system is represented by C. So we have to find the transfer function of the system. So let's solve this one. Now we need to draw the FBD of this system. So let's represent that here in this way. Now when we are going to apply a torque here in this direction, so we will be having displacement in the same direction, that is theta. Now since it is having a stiffness of K, so that the stiffness of the system is going to resist this torque, and it will going to offer opposite torque, and that will be having value T into theta dot. Similarly, when we are applying this torque, the damping element in the system will going to resist it, and it will going to offer the counter torque, and it will be equal to when we are applying torque here, stiffness of the system will going to resist that torque, and it will going to offer the counter torque, or that will be equal to K into theta. Similarly, because of this torque, the damping element will going to offer the resistive torque, and that will be equal to C into theta dot. So now once we have drawn the FBD, we will be applying Newton's law to get the equation of motion for this system. So here that law will be sum of T is equal to J theta double dot. So this is how we write Newton's law in case of rotational mechanical system. So now sum of all the torque we need to find here. So again, in the direction of rotation, we will be considering positive torque, and opposite we are going to consider the negative torque. So here in the direction torque we are having is the applied torque, so it will be in positive T, and to resist this torque we are having torque offered by stiffness and torque offered by this damping element, but these are in the opposite direction to motion, so that's why it will be negative. So minus C theta dot minus K theta, and that will be equal to J theta double dot. So now this equation we can again rewrite as T is equal to J theta double dot plus C theta dot plus K theta. Okay, or normally it will be written as J theta double dot plus C theta dot plus K theta, and that is equal to T. So in this way we normally find this equation. Now once we got the equation of motion, we need to apply Laplace transform. So by applying Laplace transform, we can get the transfer function. So it will be J into S square. This value will be theta S plus C. Now Laplace of theta dot will be S into theta S again plus K into theta Laplace. So K is constant, and again Laplace of theta will be theta S, and Laplace of torque will be T of S. Okay, so again from left hand side we can take out theta S common. So theta S if we take common, so in bracket we will be having Js square plus Cs plus K is equal to T of S. So now we can write this equation in terms of transfer function. So that will be transfer function is equal to output. So output here is this displacement, that is theta S. So it will be theta S divided by input is the torque that we are applying. So T of S. So here we can write as 1 upon bracket Js square plus Cs plus K. So now this is the transfer function for this rotational mechanical system. So in this way we can find the transfer function for any mechanical system. So we need to get the force contribution or torque contribution of all the important element, that is mass, spring and damper. Once we got the contribution of these three elements, we can get the equation of motion. And once we got the equation of motion, by applying Laplace transform, we can get the transfer function for that system. So let's revise what we discussed today. We discussed about the translational mechanical system and its different element. Then we discussed about the rotational mechanical system, and again it's a different element that if we know, we can find the equation of motion for that system, and by applying Laplace transform we can get the transfer function for a given system. Then we take up the examples to understand the process of determining transfer function for mechanical system. So with this, I will end this lecture here.